Okay, so I kind of got cut off at the end of the last video, and wanted to continue with this example problem. What we're looking for here is the position in the room where this person can stand such that they will experience destructive interference from these two identical sound waves being emitted from these two different speakers. So basically what we're saying here is this wave is going up and down and up, and at some point is going to hit this person. And this other wave is identical. It starts going up and down and up. We want the distance, the distance from this guy to the first speaker has already been established. That is exactly 4.00 meters. If he stood exactly 4.00 meters from the second speaker, the two waves would be hitting him at the same point, both at the crest or peak of their wave, and that would be an example of constructive interference. He would actually be hearing a sound that has double the amplitude. What instead we want to happen is we want this wave to hit him at its bottom of its wave, so that this bottom and the top of this wave cause destructive interference, so the person actually hears nothing. And in order to do that, rather than standing at exactly 4.00, we want them to be standing either, so we don't want it to be at the peak. We either want it to be 1/2 of a wavelength longer or 1/2 of a wavelength shorter. So 4 meters plus or minus half of a wavelength is going to tell us the exact distance that he needs to be standing from the second speaker. So, yep, there we go. The distance needs to be 4 plus or minus half of a wavelength. Let's remind ourselves that the speed of sound in air at room temperature is 343 meters per second. And that wavelength of a wave is equal to its velocity divided by its frequency. That's an equation from the last chapter when we introduced waves, chapter 11. And so the velocity of our sound wave in room temperature air is 343 meters per second. And the frequency of the wave given in the problem statement was 1,150 hertz. And so when we divide 343 by 1150, we get 0.30 meters. So one full wavelength is equal to 0.30 meters. So half of a wavelength is going to be 0.30 divided by 2, which is 0.15 meters. So if the distance to the first speaker was 4.00 meters, we want the distance to the second speaker to be 4.00 plus or minus 0.15 meters. So in other words, this could be 4.15 meters, or it could be 3.85 meters. Either of those distances would work. That would result in destructive interference, where the crest of one wave is hitting the person at the exact same time that the bottom trough of the other, so the top of this wave and the bottom of this wave, are hitting him at exactly the same time, and they're essentially canceling each other out, and the person hears nothing. So, as I was saying before, if you've got two waves that have slightly different frequencies, they will kind of shift their relationship to each other, where at certain points they are going to experience destructive interference. These two waves are going to cancel each other out, and the result is going to be nothing. But then eventually they will come to be in the same in the same phase with each other, and so both peaks of these waves are occurring at the same time, and we'll actually then get a sound that is doubled in amplitude. So I typically share with my class this observation I don't know if this will help you or not, but it kind of helps me to visualize this. But if you've ever been stopped at an intersection and notice people's turn signals, they're different cars. The turn signals flash on and off at different rates. In other words, they have different frequencies. And if you sit there long enough and watch them, you'll notice that eventually the two different cars, their flashlights will be flashing at the exact same time. But then, because they don't have the exact same frequency, eventually they'll get to a point where they're alternating flashing, where one car flashes, then the other one, then the first car, then the other one. And that is sort of like an example of beats. You've got two waves with different frequencies that over time will shift to be opposed to each other. So this point in the graph here is almost like the point where you've got one flashing, then the other, and then the first, and then the other. They're opposite each other. But eventually, over time, because of their frequencies, they get to the point where they're both flashing at the same time. And we get this constructive interference doubling the amplitude. So that phenomenon of turn signals shifting into and out of phase with each other over time is just something that I've observed in the past. It kind of helps me visualize what's going on, because we can't really see sound waves, but we can see turn signals flashing on and off. I will post, as I said in the previous video, I will post a video to YouTube, to Blackboard from YouTube showing what this phenomenon sounds like audibly. So let's look at this example here. The way a tuning fork is used to tune an instrument like a guitar is the tuning fork has a natural frequency that it wants to vibrate at. So you strike the tuning fork and it emits a tone of a known frequency. And then you want to try to tune the guitar to match that. So like in a guitar, you've got the low E string. Maybe you've got a tuning fork that vibrates at the note E. So you want to tune your guitar to match the tuning fork. If the tune of the guitar, if the frequency of the guitar string is slightly off from the tuning fork, you're going to hear beats. You're going to hear sort of a repeated, kind of a thumping noise almost, or if I can go back here to this previous slide to kind of visualize it, you're going to hear like a increase and decrease, and increase and decrease in these tones. And you can kind of count the beats, the number of audible oscillations, if you will. And so that will give you an indication of how far off the two frequencies are. So in this example problem, we have a tuning fork that's going to produce a steady 400 hertz tone every time. It's struck and it vibrates, and then we pluck the guitar string, and we notice those two tones, when overlapping each other, create 20 of these beats. So they're like here would be the example of the beat where we're seeing this constructive interference. We're hearing those. We're hearing 20 of them in a period of 5 seconds. So what are the possible frequencies of the guitar string? Well, if we're seeing 20 beats in 5 seconds, that simplifies. 20 divided by 5 is 4. So we're seeing 4 beats per second. See up there. Okay, so 4 beats per second means anything happening per second is a hertz. So we're basically 4 hertz off of what the tuning fork is. And the tuning fork was 400 hertz. So if we pluck the guitar string and we're hearing beats at a rate of 4 hertz, that's telling us the difference between the guitar and the tuning fork. So the guitar is either it has a frequency 4 hertz too high, so it's either 404 hertz, or it has a frequency that's too low. It could be 396 hertz. Okay, so those are the 2 possible frequencies of the guitar string. If we compare the 2 tones and we're hearing some beats, we're hearing 20 beats in 5 seconds, that's 4 beats in 1 second, which means it's off by 4 hertz, either plus or minus. Some of you may have heard of the Doppler effect. The term Doppler is often used in weather forecasts when they talk about Doppler radar. Some of you may remember there was an episode of The Big Bang Theory where Sheldon dressed up as the Doppler effect for a Halloween party. But the Doppler effect is something you've probably all experienced when you hear something that's emitting a tone and it's moving. Like in this example here, a fire truck. When that fire truck is coming towards you, it's traveling with respect to the sound waves being created. And because each subsequent wave gets produced a little bit further to the right, it compresses these waves. It makes them closer together. And when waves are close together, that means they have a higher frequency. And higher frequency sounds, you can hear the difference in a higher frequency. Versus if you're standing back here and the fire truck is moving away from you, every time it creates one of these waves, then it drives further away by the time it creates the next wave. And what happens is these sound waves get spread out further apart. And so you have a lower frequency. And so you can hear that. I'll go ahead and try to mimic the sound you might hear of, like, I'll post a video. I've got a video here of a minivan driving down the road, and the person's laying on the horn, and someone's recording it from the side of the road, and they hear the van go by, and it makes that kind of sound. And that high pitch you hear at the beginning is because the source of the sound is coming towards you and compressing these sound waves close together. And then on the tail end of it, it drops down in pitch because these sound waves are spreading further apart. So this change in apparent pitch of a sound wave based on the source of the sound moving is known as the Doppler effect. And so, as I said here, if it's moving towards you, it makes the frequency higher frequency, shorter wavelength. And if you're behind it and it's moving away from you, then it sounds as if you've got a longer wavelength and a lower frequency. So here we have the source of the sound that's moving to the right. And so it created one wave which moved away from it at a certain speed. But then the source moved to the right to position 2 in order to create the next wave. And so these 2 waves end up getting closer together because the first one was created over here, and then the second one was created over here. And so we have shortened that distance between them. And so that's what leads to the Doppler effect. And if we look at the derivation of the formula here, well, I better stop because I'm just about out of my 15 minutes. So we'll look at the derivation of this formula in the next video.